You ever look at a huge skyscraper or a massive bridge and just wonder, how is that thing still standing? I mean, really think about it. Well, it turns out there's this invisible battle, a constant push and pull happening inside literally every object around us, and that's what holds our world together. So let's dive into the hidden physics that makes it all possible: elasticity.
And it all starts with a really simple question, one we've all experimented with. You stretch a rubber band, let it go, it snaps right back. You bend a paperclip, and it just stays bent. It seems so obvious, but why? What's actually going on there? The answer lies in how these different materials deal with an internal struggle. Right, so to get to the bottom of this, we need to zoom way in and look at that inner battle. It's really defined by two key ideas that are always in play whenever you push or pull on something. Okay, so you've got two main players here. On one side, there's stress. That's the force inside the material fighting back, trying to get back to its original shape. And on the other side, you have strain. That's the change you can actually see. The stretch, the bend, the squish. Think of them as two sides of the same coin, the internal fight versus the visible result. So let's get a little more specific. Stress is basically the force you're applying divided by the area you're applying it to. The official unit for it is the Pascal. This is the material basically screaming, "Hey, get off me, I'm pushing back." And you know, this internal fight can go down a few different ways. You've got tensile stress. That's when you're pulling something apart, like stretching a cable. Then there's compressive stress, which is the exact opposite. It's from pushing forces, like a pillar holding up a roof. And finally, there's shear stress, which is more of a slicing force. You know, just like a pair of scissors cutting through paper.
And now for that other side of the coin. Strain. Strain is super straightforward. It's just a measure of how much the material actually changes shape. But what's really cool here is the formula. It's the change in size divided by the original size. It's a ratio, which means strain has no units. It's just a pure number telling you how much something has deformed proportionally.
Okay, so we've got the internal fight, which is stress, and the visible change, which is strain. So, is there any connection between them? You bet there is. And for most materials, it turns out to be this beautifully simple, elegant rule that ties the two together.
And here's the core idea. It's really intuitive. The more you pull, the more it stretches. For a while at least, the relationship is perfectly predictable. The amount of stress you put in is directly proportional to the amount of strain you get out. It's a perfect one-to-one relationship.
This whole elegant idea has a name: Hooke's law. The formula is simple. Stress equals strain times some constant, which we call E. Now this E is the really interesting part. It's kind of like the magic ingredient that defines the unique personality of any given material.
This E is officially called the modulus of elasticity. But honestly, the best way to think about it is as a material's stubbornness rating. A really high E means the material is super stiff and doesn't want to bend, like steel. A low E means it's pretty flexible, like rubber. For things like wires, this is called Young's modulus, and it's one of the most important numbers in all of engineering.
But, and this is a big but, that perfect, predictable relationship from Hooke's law can't go on forever. If you keep pulling, if you keep adding stress, every material eventually hits a point where things start to get weird and the changes become permanent.
And this brings us right back to our original mystery, the rubber band versus the paperclip. The rubber band shows elastic behavior. It always springs back. But the paperclip, once you bend it too far, shows plastic behavior. It's permanently changed. And that distinction, right there, is everything.
We can actually map this whole thing out like the life story of a material under pressure. First, you're in the elastic region. Everything is great. Hooke's law is in charge. The material will always bounce back. Then, you hit the yield point, and that's the point of no return. From here on, any change is permanent. You're now in the plastic region, where it just keeps stretching and deforming until, finally, it hits the breaking point, and it fails. It snaps.
So why does any of this matter? I mean, who cares? Well, because understanding this entire life cycle is what separates building a hut from building a skyscraper. The ability to actually measure and predict this journey, from a simple elastic stretch all the way to its breaking point, is the hidden foundation of pretty much all of modern engineering.
And trust me, this isn't just some abstract physics concept. It is absolutely everywhere you look. From the buildings we live in, to the bridges we drive over, the planes we fly in, and yeah, even inside our own bodies with our bones and muscles. Think about skyscrapers, for instance. Why steel?
Well, engineers choose steel precisely for its super high stubbornness rating, its high Young's modulus. That stiffness ensures it can handle incredible loads without deforming, keeping that whole structure standing tall.
Bridges are an even better example. They are literally designed to be elastic. They have to flex and bend just a tiny bit under all the stress from traffic and wind, but without ever hitting that point of no return. That little bit of give is exactly what keeps them from cracking apart.
And in aerospace, the stakes are, well, sky high. The materials they use for aircraft have to be able to handle unbelievable stress from pressure changes and constant vibration, all while staying safely inside their happy, elastic region. And it's not just things we build, it's us. Every single time you walk, or run, or jump, you are depending on the natural elastic properties of your bones and your muscles to absorb that shock and spring right back. We are, quite literally, walking, talking elastic systems.
You know, when you boil it all down, it comes back to this one fundamental truth. This quote just nails it. Elastic behavior isn't just some theory in a textbook. It is the absolute foundation of modern engineering and all of our technology.
So from a simple rubber band all the way to the tallest skyscraper, the exact same rules are at play. Now you can see that invisible dance of stress and strain that's holding our entire world together. So the only real question left is, now that we know the rules, what are we going to build with them next?